recording? Yes. Okay, so here we are. I'm going to do some stuff. Nobody's going to watch this anyway. Who cares? So, right, quit. Get out of here. Run, cargo, run. Here they are, those spaces for a... Yes, very nice. So, I shall now... Let's try... Oh, I'm floating. Who did that? Ugh. Okay, let's have console. I don't have console. Well, poo. How about Q terminal? All right. Ooh, that's hideous. Okay. So we're gonna go to. Oh, I can't see a thing. All right. So that's not gonna work well. Desktop. And then what do we call this? Variables. Yeah, that. And then source. And then we will get into main dot. Oh no. Okay. Haha. Preferences. Appearance. Font. Do I have a font? Okay. Yeah, fine. Color scheme, solarized. Apply. I can survive this. Why did I even change? Is it because the colors were bad? I don't remember. Let's see, where was I? So we used the spaces. Okay. Wait, I was supposed to do it mutable first. Let's try it. So now we're going to say what? Let mute spaces here, right? Okay. So let mute spaces. And okay, it's too far up in the list. Cargo run. Oh yeah, so it says help remove this mute. Yeah, great. Well, that's... Wait. Can't mutate a variable stuff. Okay, whatever. Now that we've explored how variables work, let's look at more data types they can have. Data types. Every value in Rust is of a certain data type, which tells Rust what kind of data is being specified so it knows how to work with that data. We'll look at two data type subsets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section in chapter 2, we must add a type annotation like this. Let guess u32 equal 42.parse.expect, not a number. If we don't add the type annotation here, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Yes. You will see different type annotations for other data types. Scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the u32 type. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integer types start with I instead of u, and that takes up 32 bits of space. This table shows the built-in integer types in Rust. Each variant in the signed... Ooh, I'm yawning. Sorry. Go to sleep. The table shows the built-in integer types in Rust, each variant in the signed and unsigned columns. For example, I16 can be used to declare the type of an integer value. So integer types in Rust, we've got 8-bit, 16-bit, 32-bit, 64-bit, 128-bit, and Arch. So then signed, right? And then down there at Arch, it's isize and usize. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for the number to be negative or positive. In other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive and can therefore be represented without a sign, unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored using 2's complement representation. Each signed variant can store numbers from negative 2 to the power of n minus 1 dash 1. Yeah. To 2 n dash 1 inclusive, where n is the number of bits that variant uses. So, an I8 can store numbers from negative 2 to the 7th to 2 to the 7th dash 1. Oh, minus 1. It really is minus 1, I guess. Which equals negative 128 to 127. Unsigned variants can store numbers from 0 to 2 to the n, the minus 1. Okay, so an unsigned 8, a U8, can store numbers from 0 to 2 to the 8th minus 1, which equals 0 to 255. Additionally, the isize and usize types depend on the kind of computer your program is running on. 64 bits if you're on a 64-bit architecture, and 32 bits if you're on a 32-bit architecture. You can write integer literals in any of the forms shown in the following table. Note that all number literals except the byte literal allow a type suffix, such as 57U8, and underscore as a visual separator, such as 1 underscore 000. So integer literals in Rust with number literals and examples. Decimal, example, 98 underscore 222. Hex, example, 0xFF. Octal, example, 0o77. Binary, example, 0b1111 underscore 0000. Byte, U8 only. B, character, sort of, because we got the single quotes. Okay, so B, and then single quote, capital A, single quote. So how do you know which type of integer to use? If you're unsure, Rust's defaults are generally good choices, and integer types default to I32. This type is generally the fastest, even on 64-bit systems. The primary situation in which you'd use isize or usize is when indexing some sort of collection. Integer overflow. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the variable to a value outside of that range, such as 256, integer overflow will occur. Rust has some interesting rules involving this behavior. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the unrecoverable errors with panic section in Chapter 9. When you're compiling in release mode with the release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs 2's complement wrapping. In short, values greater than the maximum value the type can hold wrap around to the minimum of the values the type can hold. In the case of a U8, 256 becomes 0, 257. Wait. Oh, I got this. 256 becomes 0. 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflow's wrapping behavior is considered an error. If you want to wrap explicitly, you can use the standard library type wrapping. Speaking of wrapping,